First we will start with what memoryless system. So system characteristics. We will be dealing with different characteristics of the system. Or anything like this, right? So can you give an example of a physical system having this property? As electronics engineers, whenever we see such a thing, we can remember our basic laws, right? Like, say, it can be something like V of t is equal to R into I of t. V is equal to IR, right? Or I is equal to V by R. So a resistor, so this implies that a resistor is an example of a memoryless system, right? And say consider this system. Y of t output is x of t minus 1. That meaning y of t depends on the input, on the past input signal, right? So the output at this time t depends on the input given 1 second before. It depends on the input given at t minus 1. So there is the output at time t depends on input at time t minus 1. So this is a system with memory. So this is not a memoryless system. So this is not a memoryless system, and in general what happens if we have y of t is equal to x of t minus t naught, then this is we call a system with memory. Okay, so what happens if t naught is equal to, if t naught is greater than 0, then this is a delay system, right? Okay, if t naught is greater than 0, then y of t is a delayed version of x of t. Do you agree? So the output is simply the input delayed by some time t naught, if t naught is greater than 0, right? So that's why this is called a delay system. So a delay system is a system having memory. Okay, so here why do we call it memory? Like so now you can understand it's not at all confusing, right? For the system to produce output at time t, it should remember the input given at some time back. Say for example, for this system to produce output y of t at time t, it should remember what is the input given at time t minus 1. It should store that information, or it should retain, or it should store, or it should have a memory of what was the input 1 second before, right? Because the input is being given continuously. Input we give x of t, so x of 0, x of 1, and so on up to x of t. Then the output at time t is depending on the input at time t minus 1. So the system has to remember or memorize the input at some time back. So that's why we call it a system with memory. And then let's see some more examples. Okay, so in the same system, so if t naught is less than 0, say if t naught is minus 5, then y of t is equal to x of t plus y of t is equal to x of t plus 5, right? If t naught is less than 0, then the system advances the input signal in time, right? If t naught is greater than 0, the system is delaying the output signal. The output is a delayed version of the input signal, and if t naught is less than 0, then the system advances the input signal, right? So as per our definition, both y of t is equal to some x of t minus say 3 and y of t equal to x of t plus 3, or in general y of t is equal to x of t minus t naught for both t naught greater than 0 and t naught less than 0, is a system with memory. So you should remember one thing: whenever the current output depends not only on the input at that value at that time, then we should say such a system as a system with memory. And say let's another example is y of t is minus infinity to t x of tau t tau. So what is this system? Memory, a system with memory, or system with memoryless? Now you can say this readily, right? Like if you just look at the input output relation, you can understand this. Y of t, like the output at time t, depends on all the previous inputs from minus infinity to t. We are just summing up all the previous inputs, right? It's integral of minus infinity to plus infinity x of tau d tau. So we are it's kind of an accumulator. It sums up the input signal given till that point. So it is a system with memory. Right. So can you give one physical example? one component having this kind of property? Again, as electronics engineers, you can think of your components like uh, resistor, capacitor, inductor, right? So as you can guess, some of you must have guessed by this time that uh, what is this? There is something like V out 1 by C integral minus infinity to T I of t dt, right? Or Q of t dt, like verify this. So a capacitor is a system with memory. Okay, so we studied what is a system with memory, and in terms of now we want to say that in terms of impulse response. How do we say whether now consider an LTI system having an impulse response h of t, right? You are given a linear time invariant system having an impulse response h of t, and then you are asked to determine whether the system has memory or not. How do you do this? So let's see that. Now let's write the equation. Y of t is minus infinity to plus infinity, x of tau h of t minus tau d tau, right? And for a memoryless system, we want y of t is equal to some constant or some k multiplied by x of t. So you think of what do we need for h of t so that we will get this output, right? See, we know that this is the input output relation of an LTI system, and we want this y of t. So we want this y of t to be equivalent to k into x of t. So in that case, what should be this h of t? So if you do some reverse engineering, it's very trivial. You can do it in like in one step, or you can just guess that when h of t is delta of t, a unit impulse response, when h of t is equal to k into delta of t, then y of t is minus infinity to plus infinity, x of tau k into h of t minus tau d. Sorry, yeah. So instead of h of t minus tau, I should write here as delta of t minus tau d tau. So that is equivalent to k into x of t. Because this delta of t minus tau is 0 for every value of tau except at tau is equal to 0. Since delta of t minus tau is equal to 1 at tau equal to t and it's 0 0 otherwise. Hence, this becomes this, right? It's a simple integral, right? Like we kind of doing reverse. We are kind of doing reverse engineering. Like we know what should be the output. So this is the output equation, and we know that for this system to be memoryless, we want y of t to be equivalent to k into x of t, and then we are guessing that when h of t is equal to k into delta of t, then it becomes a memoryless system. So the same thing we are verifying. So that means for an LTI system, for an LTI system to be memoryless, its impulse response h of t should be equal to 0 for t not equal to 0. Just to state h of t to be 0 for t not equal to 0. Because that's what h of t, right? Like say here h of t is equal to delta of t, k into delta of t. What is delta of t? Delta of t is non-zero only at t equal to 0, and it is 0 everywhere else, right? So delta of t is 0 at for every value of t except for t equal to 0. So for a system to be memoryless, its impulse response should be 0 at all values of time except at time t equal to 0, right? So if you have any questions, you can ask me. So in terms of impulse response, we can say that you look at the given impulse response of the LTI system and see whether it is 0 for all non-zero values of t, and say whether it is a memoryless system or not, right? So this is for the memoryless system property. Now let's go to another characteristic of the system, which is invertibility and inverse systems. Invertibility of a system. So when do we call a system as an invertible system? And what is an inverse system? When do we call a system as an invertible system? So first of all, what do we mean by invertible? So there is a system. We have given some input and we got some output, right? So from this output, if we can get back the input, we call such a system as an invertible system. So from the given output, if you can get back to the input through some other system, of course we need to process. Say for example, in communication, all communication systems are kind of invertible systems, because when we transmit some information at the transmitter, at the receiver, you are trying to get back that original information transmitted at the transmission, right? So if we can get back the input from the output, then of a system, then such a system is called invertible system. And when, if we can get back, if we can obtain the input signal x of t from the output signal y of t, then such a system is called an invertible system, right? So for the invertible system, the system should produce one-to-one mapping between the inputs and outputs. So the system should, that means an invertible system provides one-to-one mapping. See, strictly speaking, like, in fact, a more higher level of viewing a system as simply a mathematical function. The system is a mathematical function which maps inputs to the outputs. If you are more mathematically inclined, and if you want to think more mathematically rather than using the physical devices or physical units, then a system is nothing but a mathematical function which takes inputs and maps it to some output. So an invertible system provides one-to-one mapping between its inputs and outputs, right? Or in other words, for distinct, okay, another way of saying this is distinct inputs lead to distinct outputs. Distinct inputs lead to distinct outputs. So okay, say y of t is equal to some k into x of t. Does it provide one-to-one mapping between input and output? Does it provide one-to-one mapping between input and output? Yes, because y of t is k into x of t, so it's invertible, whereas y of t is x square of t. Y of t is equal to x square of t. It's not an invertible system, because say x of t equal to +4 or -4, both gets mapped to plus 16 here. When x of t is equal to minus value or having plus value, both gets mapped to a positive value by this relation. So this is not an invertible. This does not provide a one-to-one mapping between its inputs and outputs. Whereas this system, y of t is equal to k into x of t, there is a one-to-one mapping between its inputs and outputs. So this is, in this case, the distinct outputs lead to distinct inputs. Sorry, distinct inputs lead to distinct outputs. Right. So this is an invertible system. Yeah. So when what is an inverse system? Okay. So we have a LTI system having its impulse response as h of t, and we have given its output, sorry, its input as x of t, and it has produced its output as y of t. Then an inverse system for this LTI system is having an impulse response h I of t. See here, this I stands for inverse, right? And its output, let's say w of t. So this w of t, if it is x of t, okay, so let's not write here. So when w of t is equivalent to x of t, we call hi of t as the inverse system, as the impulse response of the inverse system to the system having its impulse response as h of t. See, in sentence, it looks a long sentence because I need to be correctly portraying the thing in words. I keep writing long sentences, but you can understand its meaning very easily without writing these long sentences, right? See, anyway, I'll send you these notes as a PDF. So, uh, of course, it's always better to take notes, but you just try to understand the main points and then note it in a short way in your notes, like rather than writing all whatever I have written on the board. So you can just focus on the key important things. So what I'm trying to say is, so there is a system which takes inputs as x of t and it produces output y of t. So from this y of t, if I can get back x of t through a system h I of t, so I'll give this y of t as input to a system h I of t, and then I'll get some output, right, w of t. But if this w of t is equivalent to my input x of t, then we call hi of t is an inverse system to h of t, right? So then we call hi of t as an inverse system to h of t. So as per this, that meaning that if we give x of t and if the first system is h of t and the second system is hi of t, output we are getting x of t, right? So that meaning h of t, when it is cascaded with its inverse, it will give back the original signal x of t. This implies that h of t convolved with hi of t should be equivalent to delta of t, right? So what I'm saying is that when we are given h of t and asked to find its inverse system hi of t, so h of t is the impulse response of h of t is the impulse response of one system, one linear time invariant system. We are given that h of t, and then we are asked to find hi of t, the impulse response of its inverse system. Then we need to find hi of t such that h of t convolved with hi of t is delta of t. See, do you understand why do we need delta of t? Why do we need delta of t? If the impulse response of a system is delta of t, its input is equal to output, right? If if I give you an impulse response of delta of t, if I tell you that there is a system having an impulse response delta of t, then its output and input are exactly the same. Whatever input you give the same output. So for our, right, so uh, here maybe I'll write if h of t is equal to delta of t, then y of t is equal to x of t, because y of t is x of tau delta of t minus tau d tau, that is equal to x of t. So a system having delta of t as its impulse response is called an identity system, because its input is equivalent to output or its output is equivalent to input. The system does nothing. It is just an identity system, right? Okay. So let's do one example of an inverse system. So if we are given h of t of an LTI systems, how do we find its inverse system? Simply find an impulse response such that h of t convolved with hi of t is equal to delta of t. Let me see what example. y of t is equal to x of, maybe, yeah, I'll take x of t minus 1, right? So it's a delay system. Mm, yep, yeah. So let's try to find out its. Okay, I just want to see what did we see. Okay, okay. So let's, we are given an LTA system. The system, if the system input is x of t, its output is x of t minus 1. If you give to the system x of t, then the system gives you an output x of t minus 1, a delayed version of the input. Then we were asked to find its inverse system. So as I said, we have to first okay, first find h of t, that means impulse response. Of the system. So how do you find impulse response? See, this is, see, while discussing something else, we have come across what is an identity system, right? Similarly, now we will discuss how do we find impulse response when we are given the input-output relation. See, this is called input-output relation. Y of t equal to x of t minus 1. What I am saying is that whatever input you give to the system, its output is whatever input x of t you give to the system, its output is the delayed version of it. Its output is x of t minus 1. So how to find, how to find h of t? Give delta of t as the input, and observe the output, right? See, what is h of t? H of t is impulse response. Impulse response. It's the response to unit impulse. H of t of a system, or impulse response of a system, is the response given by the system to an unit impulse applied at the input. So now if you know the input output relation, so as I said, this is called input output relation. So any such equation is called input output relation. Now what is the input output relation? Y of t is equal to x of t minus 1. Now to obtain h of t, give delta of t as the input. So that meaning x of t is equal to delta of t. So what is y of t? So y of t is equal to, yeah. So when you y of t is equal to delta of t minus 1. But the output, that implies h of t equal to delta of t minus 1. Is this correct or not? See, the output of the system when the input is delta of t is called the impulse response. So we have made our input as delta of t. So its output is equivalent to the impulse response. So the impulse response of the unit delay system. So this is a unit delay because the output is delayed by 1 unit corresponding to the input compared to the input. So if you look at y of t equal to x of t minus 1, this is the output is the input delayed by 1 unit. So it's called a unit delay system, right? So okay, now we need to find what is hi of t. See, for this example, it is very easy to find inverse system. You can simply guess, right? So when there is a system which is delaying the input, then to get back the input, we have to advance the input. So we claim that hi of t is equal to delta of t plus 1 is the input, is the inverse system. Let's say this is the inverse system, right? So how do we verify this? See, how did I write hi of t is a delta of t plus 1? Because just from intuition, when a system is delaying the signal, its inverse system should advance the signal, right? So let's verify that h of t convolved with hi of t is delta of t. How do you verify that? Minus infinity to plus infinity, h of tau, hi of t minus tau, right? T minus tau plus 1. Yeah, so we can write this as, so hi of t minus tau d tau, that is nothing but h of tau is delta of tau minus 1, and this is delta of t minus tau. So t minus tau plus 1 d tau, t plus 1 tau is equal to, so it's non-zero for tau equal to t plus 1, and if you do this, you will get delta of t, because you just put tau is equal to t plus 1. If you put tau is equal to t plus 1, this is t plus 1 minus 1, that plus 1 minus 1 gets cancelled, and you finally get delta of t, right? Okay, so this is how we verified. So an inverse system, an invertible system is one which provides one-to-one mapping between its input and output, or distinct inputs lead to distinct outputs. So whenever a system provides one-to-one mapping, or whenever a system provides distinct outputs for distinct inputs, we call such a system as an invertible system. And then how do we find inverse system? Say if we are given a system with its impulse response as h of t, we have to find its inverse system. We have to find an impulse response hi of t, which when convolved with h of t results in delta of t, right? So, this is how we find inverse systems and test whether a system is invertible or not. Causality, or we can simply call it as causal systems, right? So when yeah, so if at any given time the output of a linear time invariant system depends on the input at its current value, at its current value and the past values, it's called a causal system. Say, okay, to say in other words, the output should depend on the present and or the past inputs, not on the future inputs. So such a system is called causal inputs. First let's write its definition. Then so system is, so causal is CAUSAL, right? It's not casual. It's causal. A system is causal if it's the output is the output at any given time. At any time depends on values of the input, depends on values of the input at only the present and the past times. So that means y of t depends only on x of t and x of t minus t minus 1, t minus 2, and so on, or t minus t naught for t naught greater than 0. Okay, so almost almost all the systems that we see that we come across are causal systems. Say one of the simplest example of a causal system is a, is a car or van or okay, so let's call it as an automobile. Say in an automobile, the output, the velocity or the direction of the car depends on the current input and at most the past inputs, but not the future inputs, right? Say for example, the response of an automobile The response of an automobile depends on the inputs given till that point of time by the driver. So the inputs can be the accelerator, brake, or the steering direction, whatever, right? So the output depends only on the inputs, the current input and the past inputs. So such a system is causal, and the automobile will never anticipate, will never imagine what will be the future inputs from the driver, and accordingly it will move, right? So it will not anticipate the future inputs. It will act on the inputs till that point of time, given till that point of time. It will never anticipate input for the future. So, such a system is also called, this such a system is also called a non-anticipative system, because the system does not anticipate future values. Because in deciding its output, the system does not anticipate the said the response of an automobile will never depend on the future inputs to be given by the driver. It depends on the inputs given till that point of time. That's it, right? And so another example is this, your RC circuit. Say there is a resistor and capacitor. So V in of T, this is V out. Say this is the input, and this is the output, right? So the output depends on the input only till time T, not on future values of T, not on the future input voltage. It depends only on the input voltage given till that point of time, not on the future voltages. So this is R and C. So this is one example. Another example, as I was saying, is automobile system. So another simple example is y of t is equal to so y of t is equal to some k into x of t. This is also a causal system, because the the, the, the output is not depending on the future inputs. So for a causal system, the output will not depend on future, the output will not depend on future inputs. Now let's say this is y of t is equal to x of t plus 1. Yes, this this is a non-causal system. So this is not a, so this is not a causal system, right? And what else we can say about? Okay, so say for example, okay, another point that we need to say about causal systems is, say for example, if a system is causal, can we say this? So consider a causal system. Consider a causal system. Consider a causal linear time invariant system. Of course, we are considering all linear time invariant systems, but let me be more specific. Consider a causal linear time invariant system. System having impulse response. And say we have given an input x1 of t and we got an output y1 of t. And now let's imagine the same system with an input, a different input x2 of t, and then its output is y2 of t. Okay, so we have a causal linear time invariant system. If I give input x1 of t, I get output y1 of t, and if I give input x2 of t, I get output y2 of t, right? So if x1 of t is equal to x2 of t, so if x1 of t is equal to x2 of t, for t less than or equal to t naught, some value of t naught, then y1 of t is equal to y2 of t for t less than or equal to t. So this is another property of a causal linear time invariant systems. Why? See, this property is very simple to understand. See, the output, we are saying that h of t is a causal linear time invariant system. So that meaning its output y1 of t depends on its input x1 of t till that point in time. Similarly, if I give the same input, I should give the same output, right? So that's simply the explanation for this. So if I give the input, if these two input signals are same for the time duration from minus infinity to t naught, then its output signals will also be the same for the time duration from minus infinity to t naught, right? So that's another thing. And then we will do two more examples on this, and then we can stop for today. Like two more examples are so these examples are okay. So let's consider y of t is equal to x of minus t. Causal or not. You can think about it in 2 minutes and then we can discuss. Okay. Yeah. You can discuss with your friends or you can say whether it is a causal system or not. Right? So let's examine for so that means y of 1 is equal to x of minus 1, y of 2 equal to x of minus 2 and so on. So that meaning the output at time t equal to 1 unit or time t equal to 1 second depends on the input at time t equal to minus 1 seconds. So that means the output is depending on the past values of the input, right? So in this case, output depends on past values of the input. Fine. So that's what we call a causal system. Okay, but let's not jump to conclusions right now. Let's not decide the conclusion right now. Now let's examine for t less than 0. That meaning y of minus 1 is equal to x of plus 1, y of minus 2, okay, I can write it down. Minus 2 is equal to x of plus 2 and so on. Now see the output of the system at t equal to minus 1 depends on the input at t equal to plus 1. So the output depends on future values of the input. So here output depends on future values of input, because right now I want the output at t equal to minus 1, but that output is depending on the input at time t equal to plus 1. So that means I am at minus 1 and I have to know what is the input signal at plus 1, right? Similarly, if I am at minus 2, I want to know the input signal at plus 2. So that means this is the output depends on future values of the input. So the system y of t is equal to x of minus t is not causal. So what is that we can learn from this example? You should not look at only time t equal to, or you should not look at only for some times. you should not here, if you look at the system for t greater than 0, then it is a causal system, right? So you should not look only for time t greater than 0 and then declare that this is a causal system. You should also look at time t less than 0. That means you should ideally look for the entire timeline, like minus infinity to plus infinity. If at any given time, if it is not behaving as a causal system, you should not call it a causal system. If at all times it should be a causal, then only it is called a causal system. If at all times the input, if at all times the output does not depend on future values of the input, such a system is called a causal system, right? So this is one interesting example. Another interesting example is this. Okay. Y of t is equal to so is this system a causal system or not? Right? How many of you think it's a causal system? How many of you think it's a non-causal system? You can quickly discuss with your friends and then you can say it. It takes only 1 minute to answer this, like 1 or 2 minutes max. So see, just carefully look at this. Some of you might be thinking that as there is a term t plus 1 here, it's not causal. No, the answer is it's a causal system. It's a causal system because y of t is x of t. So this is the input signal, and it is multiplied by some another function of t. So that another function of t is it happens to be where this f of t is cos of t plus 1. So this is some other function, and it is not the input signal. This is not the input signal. This is the input signal, right? So as y of t depends only on the current value of input, it's a causal system. You should not simply declare that on the right hand side there is a term called t plus 1, which that means its output depends on the future values of the input. That you cannot jump into conclusion, because it is still depending on x of t, not on x of t plus 1. Yes, here if it is x of t plus 1, then it's not a causal system, right? Okay, so now so we discussed what is a causal system and some of its examples. Now, in terms of impulse response, say for example, if I gave you the impulse response of a linear time invariant system, and if I ask you to find out whether the system is a causal system or not, right? So if I give you the impulse response of a linear time invariant system and ask you to find out whether the system is causal or not, how do you do that? So let's find out y of t equal to x of tau h of t minus tau d tau. Okay, so maybe for this purpose it's better to write this as minus infinity to plus infinity x of t minus tau h of tau d tau. Right? So for the system to be causal, we don't want output y of t to depend on x of t minus tau for tau less than 0. See the equation. I'm again writing it minus infinity to plus of x of t minus tau h of tau data. Right? So this x of t minus tau, this tau goes from minus infinity to plus infinity. Right? This tau varies from minus infinity to plus infinity, and for tau less than 0, x of t minus tau corresponds to future values. I'm writing it all wrong. Corresponds to future values of input signal. And we don't want that. So we don't want the output to depend on future values of the input signals. That means we don't want it to depend on x of t minus tau for tau less than 0. So this requires h of tau to be 0 for tau less than 0. That's it. You just think about it. See, this is the output equation, and we are looking at the output at time t. So when we are looking at the output at time t, as per this equation, the output is depending on x of t minus tau, and when tau is less than 0, that means the output is depend on the input, the future input values. We don't want the output to depend on the future input values. So we don't want this x of t minus tau for tau less than 0 to contribute to the output. So we want, that means h of tau to be 0. So when h of t is equal to 0 for t less than 0, that LTI system is a causal system. You can see, you can go back to the previous examples of a causal system and then find its impulse response and then see whether it is 0 for t less than 0 or not. Right? Okay, then we'll the final point to be discussed is stability, whether a system is stable or not. But I think we still have 4 minutes time. But we can do one simple example. We'll discuss the stability in the next class. Okay, so example. Say for example, there is a system whose output is always 0. Right? Whose output is always 0. So there is a system, linear time invariant system, whose output is 0 no matter what you give. So this is equal to y of t. So do we call such a system invertible system or not? Right? This is clearly not an invertible system. Why? Just think about an invertible system. An invertible system is the one in which we should be, there should be a one-to-one mapping between inputs and outputs. So here all the inputs are being mapped to the value 0. So whatever x of t I give, it is getting mapped to value 0. So it's not an invertible system. Right? Yeah. So I'll